So once again, a very good morning to all of you for this engineering thermodynamics course. So here in the today's class, we are going to discuss about the three important concepts, that is internal energy, enthalpy, and specific heats. So these are the three topics which we are going to discuss in the today's concept. So it is the sixth classroom discussion topic. So these are three important parameters: internal energy, enthalpy, and specific heat. So how can we define and how can we write down the internal energy, enthalpy, and specific heats in the various processes? And before studying this, why we have to study? So that is, it is very, very important to know that how the energy term is derived from the first law of thermodynamics, because we know that thermodynamics deals with the three different types of the E's: energy, equilibrium, and entropy. So the first law of thermodynamics defines the energy concept. So how can it derives the energy concept that you are that we are going to discuss? It is very, very important one. And similarly, this particular class also having two outcomes. So first one is prove that internal energy is a property of a system and enthalpy is a function of temperature only for an ideal gas. And the second output I'm expecting from you is, so define specific heat at constant pressure and at constant value and derive its units. So these are the two outcomes I'm expecting from you after completion of this lecture. And in the previous class, we studied that the first law of thermodynamics for a cyclic process is defined as cyclic integral of delta W is equivalent to cyclic integral of delta Q. It is for a cyclic process. So it is the meaning of the cyclic process. That is, here you can see any property diagram. So just I am not mentioning whether it is a PV diagram or TS diagram or pH diagram. So simply I have taken it as a X and Y. So it is a XY property diagram. So on the XY property diagram, we are having the initial state 1 and we are having the final state 2. So what do you mean by a property? So thermodynamic property, I've already told you that these are the point functions. So all the point functions are exact differentials or perfect differentials. That is nothing but, point function is nothing but it is independent on the path followed by the system. That is, here, just you can see, so to acquire the final state 2 from the initial state 1, so we are having the three different paths. One path is A, second path is B, third path is C. Now, when we said, so the given property, whenever a given parameter is a property means whenever its value will not change, whenever it follows whether it is a path A or path B or path C. That is, it is independent on the path followed, then we can say that it is a property and it is a point function and it is an exact differential or perfect differential. So that's why, so we are having 1A2B1, it is the one process, and the next one is another cyclic process is 1A2C1, that is another cyclic process. So now here the main intention is we have to prove that energy is a property, because I told you that work and heat, these are not properties because these two are the path functions, but difference of this delta Q and delta W, that is the difference of heat and work, is leading to a new thermodynamic property that is called as energy. So alone work and heat are not thermodynamic properties, but the difference of these two is leading to a new thermodynamic property. That new thermodynamic property we are naming it as energy. That constant value we are naming it as energy. So that just you go through the derivation. So whenever you are going through the derivation, we can write down that first of all we are considering the first process 1A2B1. So in the 1A to B1, we can write down that is the cyclic integral of the del Q and cyclic integral of the delta W. And similarly 1A to C1, 1A to C1, that is, it is another cyclic process, because I told you that cyclic process is nothing but initial state is restored back along the different path, not on the same path. So here you can see it is restoring back according to this particular path. So that is 1A2 is C1. So whenever you are subtracting the equation number 2 and equation number 1, So we are able to get the difference is equivalent to, it's a constant. So that constant we are naming it as dE, that is nothing but the total energy of a system. So now we can say that the energy is a property of a system. So how can we define the energy? Energy is nothing but it's the capacity to do work. And what are the different type forms of the energies? That is, the energy can be stored and energy can be in the transition. Because whenever we are discussing about the work and heat concept, we said that the work and heat are boundary phenomena and work and heat are is a transient phenomena. Transient phenomena means whenever a process is executing or whenever it is in the motion, then only you can observe the work and heat are crossing the boundary of the system. So here the stored energy in the form of the potential energy, kinetic energy and internal energy. So that's why these are the thermodynamic properties, and heat and work are not considered as thermodynamic properties. So potential energy, normally we can define the potential energy as mgh or mgz. So whenever you are taking the height is equivalent to z, then mgz, otherwise mgh. So kinetic energy, it is half of mv square. So already we studied the fundamentals of potential energy and kinetic energy. What are the formulas? Next one is the internal energy. So I told you that is the total energy is the summation of the various other forms of the energy like potential, kinetic, internal, electrical energy, magnetic energy, nuclear energy, like that. So whenever you are neglecting all other forms of the energies, this E can be equivalent to U. So whenever you are neglecting PE, KE and other forms of the energies, then total energy can be equivalent to the internal energy. So internal energy is nothing but sum of all forms of the energy within the system. So what are the different forms of the energies? That is internal potential energy in the form of the bond energy, and internal kinetic energy in the form of random motion of molecules and atoms. So next concept is enthalpy. So far we discussed about the energy or internal energy. Next one is how can we define the enthalpy? The sum of internal energy and flow work is known as enthalpy. That is, the enthalpy is defined as H is equivalent to U plus PV. That is the formula for enthalpy. So you know that U is nothing but internal energy and PV is known as the flow work. So that's why from this equation we are able to define that. So the enthalpy is the summation of internal energy and flow work. And specific enthalpy, because I told you that specific enthalpy is nothing but enthalpy per unit mass. So enthalpy per unit mass is normally the specific parameters are represented in terms of the small letters, that is the small h. So small h is equivalent to small u plus small pv. So the specific enthalpy is small h and normal enthalpy is capital H. That is the way we can differentiate the enthalpy as well as the specific enthalpy. And similarly, we can define here it is an extensive property of the system, because I told you that enthalpy and entropy are the extensive properties of the systems. So dH, whenever you are differentiating the enthalpy, so dH is equivalent to d of u plus pv, that is du plus pdv plus vdp. So for a constant pressure process, we know that dp is constant, so vdp is equivalent to 0. So dH is equivalent to du plus pdv. So like that we can write down the change in enthalpy for a constant pressure process. So the same thing, that is whenever you are having the PdV, so whenever you are differentiating, d of PV is equivalent to is a PdV plus VdP. So VdP is equivalent to 0. So that's why we are able to have delta QP is equivalent to dH. So that is the specific enthalpy for a constant pressure process. And we know that for an ideal gas, PV is equivalent to RT. So that's why H is equivalent to U plus PV. So just you replace PV term by RT. So H is equivalent to U plus RT now. So R is a characteristic gas constant. So from which you can say that enthalpy is a function of is a temperature only for an ideal gas. It is only for an ideal gas. So it is one of the important outcome what we have written at the beginning of the class, that is we have to prove that enthalpy is a function of temperature only. And similarly, how can we define the specific heat? The specific heat at constant pressure and at a constant value. So specific heat is normally defined as the amount of heat to pass through the boundary to raise or lower the temperature of the unit mass by unit degree. So because you know that the sensible heat transfer formula is Q is equivalent to MC into T2 minus T1. So here the C is nothing but the specific heat. So here we are having the two different types of the specific heats. One is the specific heat at the constant pressure Cp and the specific heat at the constant volume is the Cv. So from this equation we are able to derive the units for the specific heat. That is nothing but you know that the Q units are either joules or kilojoules. So it is the kilojoules divided by, because C is equivalent to Q by M into T2 minus T1. So Q units are kilojoules by M, that is nothing but mass is a kg. So difference of temperature is equivalent to Kelvin. So the specific heat units are kilojoules per is a kg Kelvin. So it is also I have listed one of the outcome I am expecting from this today's class. So I told you that the specific heat is normally classified into two ways. One is at the constant pressure at the constant volume. So Cp is equivalent to dH by dt at constant pressure, and specific heat at the constant volume is nothing but du by dt at constant volume. That is these are the formulas for Cp and Cv. So Cp is equivalent to dH by dt. That is, in the numerator you are having the change in the enthalpy at constant pressure. But coming to constant volume, Cv is equivalent to du by dt at constant volume. So in the numerator we are having the change in the internal energy. That is, what is the commonality is the denominator is common. That is, the change in the temperature is common. Only thing is that the numerator is changing from the change in enthalpy to change in internal energy from constant pressure to is a constant volume. So for ideal gas equation, you know that PV is equivalent to MRT, and whenever we are having the specific volume PV is equivalent to RT. So the first law of thermodynamics, for a change of a system, we can write down dE is equivalent to delta Q minus delta W, or du is equivalent to delta Q minus delta W. And for constant volume process, how can we write down the first law of thermodynamics? So since it is a constant volume, we know that delta W is equivalent to PdV. So dV is equivalent to 0 for a constant volume process. So automatically delta W will be equivalent to 0. So delta Q will become du. So du is equivalent to delta Q. And you know that delta Q is always equivalent to mCv dt. So per unit mass of the substance, it is equivalent to Cv into dt. So du is equivalent to Cv into dt. And similarly, how can we derive the relationship between the the two specific heats? That is the specific heat at the constant pressure and the specific heat at the constant value. And we know that the enthalpy definition is H is equivalent to U plus PV, and you write down the same equation in the differential form. dH is equivalent to du plus PdV plus VdP. So dH is equivalent to CVdt, because you know that du is equivalent to CVdt from this particular equation, and PdV is nothing but RdT. So whenever you are dividing the entire equation by the temperature, so you are able to get dH by dt is equivalent to Cv plus R, or Cp is equivalent to Cv plus R. And from this we are able to conclude one important one, that the difference of two specific heats is leading to a constant which is known as a characteristic gas constant. That is, R is equivalent to Cp minus Cv, or Cp is equivalent to Cv plus R. So from this we can say that Cp value is always greater than Cv, because R is known as the characteristic gas constant. So R is equivalent to Cp minus Cv. That is important relationship. We are able to get it from this particular one. So these are the concepts what actually we are going to study in this today's class. Now, based on these concepts, so what are the questions which were asked in the previous GATE examination? So the first question here I have written: a gas contained in a cylinder is compressed. The work required for compression being 5000 kilojoules. During the process, heat interaction of 200 kilojoules causes the surroundings to the heated, that is heat transfer from the system. The change in internal energy of the gas during the process is equivalent to how much? That is, dE is equivalent to delta Q minus delta W. Actually, it is 2000 kilojoules, not 200. It's a 2000 kilojoules. So it is 5000 minus 2000. dE is equivalent to delta Q minus delta W. So 5000 minus 2000, it is equivalent to 3000. So answer will be equivalent to C. So just you can make it a correction. It is 2000, not 200. So the next one, a 2 kilowatt 40 liter water heater is switched on for 20 minutes. the heat capacity for water is 4.2 kilojoules per kg Kelvin. Assuming all the electrical energy has gone into heating the water, increase of the water temperature in degrees centigrade is equivalent to how much? So once again, it is according to the first law of thermodynamics. So the answer will be 14.3. You can solve on your own. So it is also the another question. A bullet weighing 10 grams travels in a horizontal direction. It enters a stationary object at 350 meters per second and exits at 200 meters per second. The object does not move. Considering the stationary object as a system, the energy interaction is equivalent to how many joules? So here the answer is 412.5. Now you can do on your own. So similarly, you can do the another question also, because all these are based upon the internal energy concept, the change in the enthalpy and the specific heats and the first law of thermodynamics only. So it is the another question. So for this, the answer is minus 230 kilojoules. So like this, you can answer the few questions which were asked in the previous GATE examination based on the internal energy, enthalpy and specific heats. I hope the concepts are clearly understand to all the students. I wish you all the best, and once again we will meet you in the next class. Thank you once again.